Michael Yashin. He will be discussing reverse engineering of binary formats with the use of Kaitai Struct. Thank you for the introduction. My name is Michael Yakshin, and first I would like to introduce ourselves and why we're engaged in doing what we are doing. My company, White Box Labs, makes controllers for aquariums, terrariums, hydroponic beds, for beer brewers, cheese makers, wine makers, all kinds of closed ecospheres. There is also aquaponic, which is about having aquariums with fish installed in homes, which fish eat grass which are inside those aquariums. Which fish can be eaten by home residents and forth, which may be a very interesting source, unlimited source of food for, say, developing countries. Just a few words about what is controlled by controllers in such closed systems. There are a lot of sensors such as water level, leakage gauges, detectors, temperature gauges, water control gauges, which is very important for aquariums, for which it's crucial to be able to be in control of pH, dissolved oxygen, and so on and so forth. Flow sensors, humidity gauges, lighting sensors. We have to be in control of our light bulbs, the lighting systems that we use to light our aquariums, terrariums, and so on and so forth. For some aquariums, which are used for decoration purposes, it may be necessary to install cameras for owners to be able to enjoy their fish remotely. Since all such systems are really expensive, it would be a pity if all the fish die while the owner is on vacation, for example, which means that there should be redundant power supply systems, which in turn need to be controlled. According to studies, such sensors help to control various actuators such as pumps, dosers, sources of lighting, heaters, automatic feeders for fish skimmers, reactors, ad hoc chemical devices which are in charge of sanitating the environment in aquariums, various relays, power bars that may be in charge of supplying power to various devices. There may be more complex power control systems, which is relevant for bigger aquariums, the size of oceanariums and so forth. Challenge number one that is encountered by a typical user, customer who may want to install an aquarium, smart aquarium in home, is vendor lock-in. What is it about? There are about 5 major vendors manufacturing aquarium systems. You may buy a controller, Neptune controller for example, which means that it will only be compatible with other Neptune equipment, which systems are not cheap. Having bought several thousand euro worth of devices, such a customer will be reluctant to switch to a competitor's product because they will never be compatible with initially bought systems, being the same sensors or dosers or other devices because of being based on proprietary protocols, for example. We do not manufacture our own sensors. We're a relatively small system. However, we manufacture a controller that is compatible with all the third-party products. And we achieve that through reverse engineering of proprietary protocols and implementation of those protocols in our controllers. Now to the main point of my presentation. And I'm going to start from a general overview of the task, namely a reverse engineering of binary data structures, what we start from, what we do, what we seek to achieve, how it is done traditionally, how it is done now. I apologize in advance for repeating myself from time to time. Probably some of my points may sound trivial, however, to make the picture full, I will make them. What is normally reverse engineered? For us, communication protocols are particularly interesting for the reasons above, because those protocols are used in controllers and devices they control. Very often, it is very interesting to explore embedded firmware, the software embedded in various systems for which there are no source codes. For example, we may need to explore the algorithms there based on examine their safety. Sometimes it is necessary to attack them or to protect them, to enrich them with additional features and so forth. Next, the various container file formats. Interestingly, internally, the files, such as text files or various source codes, source files, are enclosed in containers based on unknown formats, and it may be interesting to explore those formats for compression, for indices. Now, various executable files. They can be executables or bytecodes. Normally, the bytecodes are based on formats which very often are complex enough. In modern executables, they normally have sections with something embedded. They are based on their logical structures. In order to understand what's in the file, in order to extract some resources from it, or modify it, or engage in doing some more useful work with the use of disassemblers, it is necessary to understand the structure of the file to be able to analyze it for malware and so on. Now, working with content files such as databases, tables, plain text, graphics, textures, well, the range of text may be really broad, including extraction of content files from games, or reference catalogs, should such content be in an unknown binary format for it to be reused, not just to copy it from screen, but to obtain it very quickly in machine-readable format. I can distinguish between two main approaches. But today I'm going to focus on the approach which is on the right-hand side. It is about exploring the code. If the code is available, it should be loaded to a disassembler. Well, the second approach is exploring the data proper to understand what's in there, to identify patterns, which patterns can be analyzed and implemented in order to be able to read processors for such formats. Based on our experience, I can say that only the second approach is viable for us. Why? Firstly, there is a number of licensing constraints. We would hate to find ourselves in court. We don't want lawsuit to be set forth against us. Moreover, sometimes this approach is the only possible. If the number of devices is big, we may not have a board, for example. There is just a spot on a board and we need to extract firmware somehow. How do traditional explorers work? They can work with files or file systems or disks or disk arrays. For example, once I encountered a situation where, well, it happened some 10 years ago. We were given a broken disk array for at least some information to be extracted from it. And we had to deal with its block system, and it required some kind of reverse engineering. Various boards, well, in order to be able to extract data from various kinds of memory. Now, intercepted traffic, 90% of time is normally spent on it. Everything will be in the pickup format. Only in 1% of cases will you encounter a different format. What do we want as an output? What do those engaged in reverse engineering want as an output? Normally, it is a format description, but there is now a standard format. There is no standard for such format description. Normally, C-like approaches are used. Sometimes people try to use various tables showing the distribution of bits and bytes in the memory. You can have a look at the RFC illustrating the popular PNG format. You can also see here the signatures described as chunks. You can see this type of bytes here and there. Another example, this RFC is about the UDP protocol. The developers of RFC decided to present everything here as a table, and we can see the structure of a UDP datagram as a table for 32 bits somehow, probably to fit the page. But anyway, it can be used. Now, this is description of the popular ELF format, which is a popular format for storing the content of executable files. It is presented as a series of text paragraphs with inserts. In some 80% of format descriptions that I have seen, people engage in developing substandard formats, and the standard was only passed some time ago to define various length variables, 1 byte, 2 bytes. The developers of this decided to use the word L32 half or off. One should find the section in the standard describing it, regarding the functionality of this byte, what it is about, and so on. Another very funny approach, some of you may be familiar with it. A format can be described as art. When posters are published, it can be printed out and put on a wall. The one engaged in reverse engineering is always expected to produce a parser or a decoder to parse the code. Well, everything is moved to the memory and distributed between the named cells. On the slide, you can see an example of such parser written in the C language. What can be seen here? Individual structure elements are read here, one by one, and for each reading, a certain subprogram is used, which either reads the byte or a word of a certain length with all the proper checks, with the return of the correct program type. Ironically, there is no standardized library. In some 95% of cases, people write their own libraries for this. And what you see here is an animation loading project. It is a gaming engine for which such library with SD prefixes was created. And all the way around, people normally want to obtain generators or encoders to assemble everything back, and from all those cells we make up some file. Well, everything goes in the opposite direction. In the same way a library is written, a code is written to complete such a transformation. These two slides are very much alike, as well as the code. There is traditional approach to such clear room engineering. The engineer studies a dump for a long time, comes up with hypothesis saying that these cells may contain this or those cells might contain that. If it is simple hypothesis, it is just checked manually to make sure that the frontiers of those structures are aligned, should format be slightly more complex, a parsing code is written to do what you saw on the previous slides. However, it's not uploaded to the memory. Instead of that, it is uploaded to some debugging stdout to check the hypothesis, which is an intermediate program designed to transform the to visualize the incoming file. For the purpose of hypothesis checking, in 90% of cases, it is found out that the reading means is not ideal for a reading from the flow. And later, in a minute, I will show why this project. It is not a trivial task putting all those variables in one line with ending, transformation, and so on. With this, we end up with yet another library. We compile, we start, we check our hypothesis for this particular program, and we repeat it many times until we find answers for all questions, or until we find ourselves in front of an obstacle we cannot eliminate. What kind of means are available to those who want to do this work? 99%, if not 100% of those present here have seen hex viewers or editors at least once. Nevertheless, I'm going to demonstrate it to you. This is our great Russian hue editor. Sometimes it's used. That's what we can see and meditate in front of. Prior to proceeding to more sophisticated tools, I will allow myself to give you another example that I'll be using in order to illustrate how those tools work. I'm going to use the format of the game Doom WAD, which is one of the simplest container formats. It was used in really ancient games. The original development was done between 1992 and 95. You will find a lot of borrowed code here, borrowed from earlier projects. The format itself is pretty simple on the one hand. On the other hand, it illustrates all the interesting elements that can be encountered in our container format. We have magic here, which is kind of a signature. The 4 bytes from the beginning of the file, they are letters identifying our file. If those letters are not present there, the engine will send an error message. Then in the header, we see a 4-byte field with our index elements, or the number of files in our container. There is also a shift indicator, index offset. The index itself is not directly linked with the header. It does not follow the header. With this index underscore LFS, we can read our structures. 8 plus 8. 16 byte long, One structure corresponds to one file. When reading the file, the engine first reads it complete to know which files it has and to know where to look for them. However, at this stage, the engine does not read the files themselves. With proper parser of this format, one should not read the content of the files, all the files that are present in the container, until they are really needed. The files themselves are shifted as it is mentioned in the field. They can be found with one SIG. Since the main platform is DOS, Intel DOS, it is pretty simple. Another example of more advanced software, which is software of a high level. And here we need something more than just checking our hypothesis. There are hex viewers and editors with templates. You can see some 7 of them. And in total they are between 10 and 20. Those two highlighted green, the two highlighted green are those accounting for some 80% of this market. They are 010 editor and hexinator. Well, the first one, the former, is currently passing it over smoothly to a hexinator. There are other viewers and editors with templates too, but there is no point in discussing them now.
Sweetscape. I beg your pardon for a typo. It should be 0100. It looks like this. So the difference between from a dumb hex editor is that apart from the hex dump and some representation of this hex dump in symbolic form, we also have a tree of structures marked within this file, so we can move in that tree. We generate this tree using this kind of code. This is an absolutely imperative type of code, and please pay attention to that. We create two structures, the header structure and the index entry structure. And then we're saying that first we have a header, and we do it imperatively by calling some function to move, and then assign the file entry array. The hexinator looks similarly. That's also a dump, also a tree that you can take a look. The hexinator has a tree editor that, on the one hand, should simplify the task of describing the format, but on the other hand, in my opinion, it's sometimes easier to do it direct from the keyboard than using this editor. The grammar is the same. Looks like this, both for the file, template, and hexinator. The hexinator is just a bit more declarative, more verbose. It has certain elements of the capability to take some structures out of this format and reproduce them separately. Outside this main tree. So what's good about these hex editors? They show the tree of objects and their values right in the live file with examples, things like that. In some of these editors, there's a visual tree editor, and they show which places in the binary stream objects take. So what's bad about them? The first and most important thing is the imperative character. For 101, it's 100% imperative. It's a C-like language, as we've just seen. For most others, there are attempts to implement a declarative language, but once it lacks in functionality, developers solve the problem in a very simple way. Using XML or some other format that describes the grammar, they insert a tag where they insert a script in Python or JavaScript that does the dirty work that the declarative format couldn't do. Focus on the representation. In the layout file, attention is given to colors, comments, and things like that, but you don't actually use it or value it when it's about the formal description of the format. These editors don't do a good job of automating. For instance, if you want to run some hypothesis on 1,000 or several thousand packets, get some statistically valid result isn't possible. So loading these packets one by one in such an editor and trying to learn something about them looks quite foolish. Almost all these editors read the file and mark it up fully in the memory. So you load it, and the container will be read, marked up, and in the process of this marking up, for instance, if we're working with some large image, DVD or Blu-ray disc, it will immediately be stored in the memory, bloat, and nothing good will come out of it. Except perhaps the octet, it's all a proprietary, closed software with all the drawbacks, the ensuing drawbacks. So with very limited ability to impact the development, trying to add some ideas. What else does a person trying to do format reverse engineering typically have? You can go towards Wireshark and other traffic analyzers. I'm sure that most of the attendees have seen such tools at least once. In fact, it looks like a dump and then some tree built out of it. And then there are pros and cons for all such tools. There are lots of Wireshark dissectors, but they are also 100% imperative, and they are very difficult to implement. Even if you want to start the investigation of a format with writing a dissector, it's usually a bad idea because it becomes too difficult to do it. There are so-called BMS, also known as MEX script, also known as binary MEX script, also known as multi-X script. It's a family of specialized scripting languages intended to derive data out of binary files. Popular in the community, doing reverse engineering of games. So this is an example of a WAD file. But again, there are two big problems about that. On the one hand, this is indeed there's indeed a good database of accumulated format descriptions. There are lots of embedded algorithms, but it's imperative and it's only intended to solve one problem. For instance, in most cases, just to take some file out of a container, and that's it. There are lots of other formats, There are lots of formats, and perhaps I'm not going to dwell on them in detail. There's the so-called bin pack, which is declarative and compiles into a C++, also extendable by C++ inserts. There are lots of academic projects written in different years, flashing once and then gone forever into the limbo. There's the so-called DevDL format. In fact, this is the closest thing to what one would wish to have and one would wish to work with. It's a declarative format, XML-like. It's trying to describe the structure. And basically, over the past few years, even some tools appeared to, to use it. But when I saw the complexity of this format, well, this picture here is perhaps only 3% of the total description of the file pickup. So when I saw that, it became absolutely uninteresting for me. So it's really too general, and it's intended for solving more generic tasks. There have been lots of attempts to create declarative descriptions of binary structures as applied to one specific language. So what do I want to present today and to share with you? Kaitai Struct that we made, as follows from all the above, is a declarative language of binary data structure description. We tried not to use imperative things. The description in the KSY format is compiled into the source code in the target language. So we're initially trying to get these so-called parsers. And now we are supporting about 5 languages at the output. And basically, there's nothing standing in the way for us to extend this list. We have a visualizer for fast format prototyping. As a rule, a developer working with Kaitai Struct does not even touch the code and doesn't write the code, the scripts, or anything else until it's required, until automation is needed, which looks very much like the tree-based visualizer from other. And KSI format is basically the same as YAML. It's easy to write alternative compilers and tools, so you don't need any special editors. One other reminder how DoWAD format looked: header, files, payload. So how can you describe it in Kaitai Struct? First, we'll need methods. The top level class is going to call DoWAD, which you can see from the ID. Then we disassemble the format, reverse engineer the format that's arrived from the Intel platform. So by default, all the integers will be little endian. And also we write a comment, a comment indicating which software is going to use this format. Then we have the sequence of attribute descriptions that go one by one. All these attributes will be read in this sequence. The beginning of the next one is equal to the end of the previous adjusted for alignment. Now let's see how the attributes look. There are 4 of them: line, 4 bytes, ASCII coding, magic, index underscore qt, assigned integer, 4 bytes, and same index offset. We have ID, the identifier that will be written in the code following the rules of the target language so as not to stand out. And examples are shown here how it's going to be written in Java, C#, and Ruby. And there's a type. It's a type indication. It can be primitive, that's embedded. It can be user-based, or it can be absent. In this case, it'll be considered to be a byte array without any interpretation. The primitive types are integer or strings. integers are presented in the following way. The first letter is unsigned or signed, U or S. Then we specify the number of bytes of this type, and if needed, so we also indicate if it's going to be a little endian or big endian. Strings, they're either known length in bytes or symbols, or there are strings that come before the terminator. In 90% of cases for zero, these are C strings, sometimes before the $sign, DOS strings, and rarely some other options. Or we read the string till the end of the stream, a file, or the current substructure as valid. So the type str and size for the known length for up to the terminator we call type strz, and as a terminator oxa up till the end of the stream type str and size eos true. Now we can use Kaitai struct instances. These are almost the same as attributes, but indicating the position from where to read. They are indicated separately. Sequence order is not important for them. And apart from other things, apart from posse type that I've already described, there are repeat and repeat expr. We can set a repeat of an attribute for some fixed number of times by indicating this in the expression. We can indicate an unended repeat up until the end of the string of the stream, and or we can indicate specify some condition. A small excursion into the expressions that can be used. Of course, it's a special language that we've introduced inside. It automatically translates in the target language, keeping the types. The syntax is similar to an average C-like language, and it can be used together with such attributes. For instance, you can say repeat expr 5. For all these languages, it will mean repeat the attribute 5 times. You can indicate repeat expr full bar, which will mean to repeat the attribute that as many times as indicated in the integer full bar attribute within the current type or class. You can specify that bar is the attribute of the next class, compare it with a T for a string, and it will correctly translate into the target language. You can create some more sophisticated conditions related to SA or ternary operator, and there are user types that are specified in the types column. It's the same declaration or announcement as in the tree root. You can use a sick instance and types, similar things, but they are implemented under classes, and you can refer to them after the task as a separate type. We can also note here an indication to I/O, root underscore I/O. This is done so that by default, within the type specified, reading should be done from the string of the same type. So we'll be running about and refer to the beginning of the index rather than to the beginning of the file. So we are specifically indicating him that we're going to take addresses from the start of the tree. It all looks quite difficult from the first glance, but in fact it isn't. So it can all be compiled. It compiles with a simple compiler call. At the input we have a case file. At the output, in this particular case, a module for Python. and you can immediately connect and use. We import, we use the static method from file in order to load the file, and after that we can address directly the fields of this class in order to read this file. We can ask the number of elements, the number of files in the container, getting it. We can ask the name, in this particular case, of file 42. We can open up a file and write the content of the file that we want into it. Or we can look at it in the visualizer, in a visualizer, and the view would be very similar to the one in hex editors. Uh, you can see the tree, you can see the dump, the location of the dump. You can move. We'll see and move between dependencies, between elements, so on and so forth. So that's basically it, I think. Thank you. So we have shown the capabilities that allow us to parse structures of fixed format with field lengths depending on attributes and computed from expressions, with conditional fields, with field repetitions, whatever from the start of the stream, with an arbitrary set offset in your own stream and in a third-party stream. Thank you. Yeah. Question. Questions are welcome. May I ask a question? Do you have the capability to process the data transformation? For instance, we have a data format. You need to unpack it, and then no. Data in some encrypted format, and we need to process as the data. Imagine they're coded in base 64. So first you need to decode it and then encode again. Excuse me, I can't translate what's being said without a microphone. Can you suggest that the speaker presses the button? Well, my question is, I'm sorry, the question. Kaitai Struct is it free software or is it paid for? It is free. Can you please suggest the speaker to press the microphone button because the interpreter doesn't hear what he's saying? This software is distributed for Apache or Met licenses. And somewhere in GitLab, do you have links where we can download it? Here it is. Thank you very much. A question. Why did you give up on TSN1? For some reason, it was absent from the comparison list. It's also declarative and quite non-trivial. Protocols use it. For instance, the entire telecom business is based on TSN1. It's a long story. To be brief, because of high complexity and less than ideal supportability by tools. So perhaps what you mean is not ISN1, but CN1 EDR. ISN1 itself, as far as I remember, firstly, it's a whole family of formats, and for the most part, SN1. When people refer to SN1, they mean all sorts of BR, CR, that, generally speaking, have almost no relation to this. These are just serialization formats, schemaless, that are carrying the schema within the format. That is, so yeah, that would be my brief answer. Is it possible to analyze the data compiled for different platforms so that the structures would be the same, but the data being represented in different ways for different platforms? For instance, Intel Spark, so reversing not only the order of bytes in one attribute, but also the entire structure. Is there any switch or a way to indicate there's a capability to use this conditional structure so that somewhere in the middle of decision making, that for instance, further we're going to have a substructure specific for Intel or Spark. So by the platform flag, it appears then. So if there's some indicator to the specific platform, the indication in a file, yes, in the data, yes. If in the data, then yes, of course. Using this flag, you can let's say switch passing to one structure or the other. Thank you. Thank you very much for your presentation. Please pick two questions that you liked most. Thank you. Well, in that case, perhaps I will award it to the guy who asked about processing. And perhaps the one to the guy who asked about conditional processing. Yeah, thank you. Thank you very much.